Right now, there is one other thing about damping that I don't want to end today, since Sean asked about damping, without mentioning. If I were to draw the amplitude with time for a lightly damped oscillation. So this is amplitude with time. Right now, I am going to mark in equi-spaced things so that it makes it easier for me to keep my frequency, my period constant, because that doesn't change. Okay, and I'm going to go like this. So I'm going to start up here, and I'm going to go like this. If I draw the envelope, okay, so this line, that envelope, it's not very, very beautifully drawn, but that envelope is exponential. So this is an exponential decay, and so is this one. Okay. Now, how can you show that it's exponential? What would you do if you were asked, if you were given this with a scale? Right, if you were given a scale for your amplitude in, I don't know, centimeters, and this is time in, I don't know, seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 seconds. Right. Let's imagine that you were given that graph. How could you show, the question says, show that the envelope for the maximum amplitude and how it's changing with time for this damped oscillation is an exponential. Half-lives. You'd think, wouldn't you, that it would be half-lives? But actually, the best way to demonstrate this is to get this value and call it A0, and this value and call it A1, and this value and call it A2, and this value and call it A3. Okay? And then, because the rate at which something changes depends on how much there is, you get the same fractional change for the same length of time, and we're going to choose one complete oscillation time, so period. We should get the same fractional change. So you can write that A0 over A1 is equal to some constant, and it should be the same as A1 over A2, which should be the same as A2 over A3, and so on. If it's exponential, those numbers will all be the same because the period that we're dealing with is the same. Can you see that the period of the oscillation is a more sensible time to use than the half-life? I mean, your idea should work, but this you can just read off the graph. It makes it easier. Okay, and this is true for any exponential. So if you were to get any exponential, you could just choose the same time over and over and over. And if you did the values on the y-axis for one divided by the other, and then one divided by the other, and one divided by the other, I mean, that's essential. It's in essence what you're doing with half-life or with capacitive decay, the 37% line, right? It's the same fractional change every time. That's what's meant by an exponential. So if this is true and it's always equal to a constant, then the decay is exponential. Okay. And lightly damped oscillations are exponential.